Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will discuss one very important aspect of the draw frame sliver, which is mass variation in the sliver. Now, whatever we do in the draw frame in the production, so if the mass variation is there, then draw frame is not performing well. So, irrespective of roller sleeve or drafting force, everything is there. So, the mass we are, our basic idea is to control the mass variation in sliver. We want to create, we want to produce a sliver with less variability. So, minimum variation is required. So, that is why we must understand what is mass variation, how to express the mass variation, how is it being calculated. So, what are the how the data is analyzed. So, that in this section we will discuss in detail. Okay. Here mass variation is actually expressed in terms of evenness. So, evenness means evenness in maybe in the diameter, evenness in the mass per unit length. So, this is one sliver and this one, our idea is to create a sliver like this, ideal. So, there is no variation, but effectively we get a sliver with a variability. Definitely there will be variability due to the shortcomings that we have discussed, the way of fiber movement during the drafting, the floating fibers. So, they create, but ideal drafting is this one, but we do not get the ideal drafting system. So, that is why we create the variability. This is the variability which is called the wave, this forms a wave, there is a periodic variation, and this one is the random variation is there. Periodic variation is generated due to the roller defect, roller eccentricity, that we will discuss, and random variation due to the floating fiber or due to different reasons. So, there are two ways we can express. One is CV%, that is standard deviation by mean, and the U%, it is which is percent mean deviation. So, if we say take a strand, a sliver, if we cut the sliver at certain length, say 1 meter length, and if we get the mass W1, W2, W3, and if we calculate the standard deviation, so up to Wn, and calculate the standard deviation, and then we can get the CV%, and U% is basically where in the evenness tester the reference length is 1 centimeter. So, a sliver if we take, okay, and if we cut each length of 1 centimeter length, then we take the mass and then we calculate the mean deviation, and mean deviation by mean multiplied by 100 is the percent mean deviation, which is expressed as U%. So, U% is, this is the deviation from mean divided by n number of reading. So, this is the mean deviation, and we express as a percentage of the mean value of mass per unit length. So, when the distribution is in the normal distribution, so about the mean, two values are related approximately. This is CV% equal to 1.25 multiplied by U% or percent mean deviation. This is the approximate value. Now, the concept of limit irregularity. Now, limit irregularity is that the term where which actually means the present system of machinery, spinning machinery, with which can produce the minimum irregularity possible. Like during drafting, the fibers are moving, the floating fibers can move at any speed that we have discussed. It is not ideal drafting. So, that will generate a minimum irregularity, say U%, minimum CV%. That is, even if we use the extremely efficient machine, very good quality machine, new machine, and we maintain the fiber quality, best fiber quality, we maintain the environmental condition, best possible environmental condition, machine setting, machine conditions are same, no vibration, still we will get certain variability, and that is due to the fact that present system where we cannot control the fiber movement positively. It is not like ideal drafting scenario we have discussed. Here the fibers move randomly depending on very large number of unknown factors. Okay. So, that is how we cannot expect the fibers will have the strand, staple fiber strand will have the 0 variability, standard deviation cannot be 0, there will be some variability, and that variability is minimum variability irrespective of the fact we are maintaining everything constant, everything ideal scenario. So, still we will get certain variability, that variability is known as the limit irregularity, and that means most uniform strand of material which our present machine can produce is one which the fiber ends are laid in random order in the sliver, roving or yarn. Okay. It is in random order, and for such a strand of material the irregularity is given by the formula. So, most uniform strand the irregularity is with the formula VR square, which is VR is the limit irregularity, minimum irregularity possible, equal to 100 square by n plus Vm square by n, where Vm is the variability, inherent variability in the fiber mass per unit length. So, for synthetic fiber like polyester and polypropylene or maybe nylon. So, this fiber they are produced through the spinneret, and the diameter or mass per unit length variation can be neglected. So, in that case Vm will be 0, okay. And there for synthetic fiber this relationship will be reduced to 100 by under root n, where n is the number of fiber in the yarn cross or fiber strand cross section, that is sliver cross section or roving or yarn. But in case of natural fiber like wool and cotton, so wool has got the variability within a single fiber, there will be variability also, even fiber to fibers the mass per unit length variation will be there. So, this fiber variability is actually denoted by Bm. So, for where the fiber variability is considered, the equation, this equation will be used, and for where the fiber variability is neglected, the equation is reduced to Vr equal to 100 by under root n. So, Vr square equal to Vm square by n, n is the number of fibers. So, number of fibers in the cross section if we increase, then limit irregularity can be reduced. So, for thicker material the limit irregularity is low. Okay. That means, for sliver the limit irregularity is lower than the roving than yarn, because sliver is thicker and number of fibers are large. So, Vr is the limit Cv of the mass per unit length, n is the average number of fiber in the cross section, and Vm is the actual Cv percentage of fiber per mass per unit length. So, mass per unit length variation is there, this is for fiber. So, for man made fiber, as I have mentioned, Vm is 0. So, Vr square is reduced to 100 square by n. For cotton, it is typically around the Vr will be 106 by under root n, okay. Because for cotton the fiber mass per unit length variability is approximately 35%. That is actually this is the average value, and it is based on the large number of specimen. So, we use this general equation for cotton, limit irregularity will be 106 by under root n. If we use this Vm here 35.16, that means we will get this value 106. Okay. For wool, similarly, wool has got the variability is much higher than cotton. So, for wool, this is the mass variability. For wool, it is approximately 50%. So, if you use the 50 here 50.44, we get the value 112, this factor. And for blend with cotton with any other fiber, it will be higher. So, why is it higher? So, if we use a polyester cotton, polyester cotton, so polyester has 0 variability, and for cotton we get 106 as per the variability factor. But when we mix polyester cotton, then it is higher than that, higher than even cotton. So, ideally it should be lower than the cotton, because what polyester is 0 and here it is 106 is the factor. So, why? Because of the compatibility. But polyester and cotton, when they mix and when the process through draw frame, their movements are different and they have their different cluster formation, different characteristics, their stress strain characteristics are different, their frictional characteristics are different. So, when we blend more than one fiber, two fibers, So, blend two fibers are there. So, they are due to their difference in their characteristics, they behave differently during the drafting session or even opening. So, that will result much higher limit irregularity. So, effectively that is why the blended product has got relatively higher irregularity than the single component product. So, for wool it is 112 square by n. When the wool diameter variation is taken, the equation is actually, it will be changed to 100 by n multiplied by this 1 plus 0.004 V d square, where V d is the variability in diameter, V m was the variability in mass per unit length for wool, approximately 50, but V d mass per sorry, it is a diameter variability, it is approximately 25% for wool we get. So, V d is the Cb percent of diameter, because wool diameters are different. So, within wool also it is changing and even between wool. So, wool, so the diameter variability is there. So, here we can use V d is approximately 25%, and if we use this 25% here, we will get the relationship, almost same relationship here, 112 square by n. For wool based on mass, where mass variability is 50%, and in case of diameter variability, when diameter variability is 25%. So, we are getting the relationship, almost same relationship we are getting. Thus, for a particular fiber and count of yarn or sliver, there is limit or basic irregularity upon which our present machine cannot improve. So, we can actually try to produce the perfect material, perfect sliver in the draw frame, but there is a limitation. We cannot try, we should not try to have the zero variability. So, for that we must understand the concept of limit irregularity. By calculating the limit irregularity and then measuring the actual irregularity, we have a means to judge the spinning performance or performance of any machine, maybe draw frame, speed frame or ring frame or any other machine. So, basically this performance of machinery. So, limit irregularity is a function of the count or linear density. So, limit irregularity, by limit irregularity or by actual irregularity which is produced, based on that we should not compare the machinery performance. For to compare the machinery performance, we have the parameter which is called index of irregularity. Before that, let us try to calculate the limit irregularity here. So, with average 100 number of fibers in the yarn cross section, the limit irregularity, so V r limit irregularity for 100% wool and 100% cotton will be. So, for 100% wool we know 112 by under root n number of fibers. So, 100 fibers are there in the cross section. So, 112 by under root 100. So, 112 by 10, 11.2, and for cotton it will be 106 by 10. So, 10.6. So, we can calculate the limit irregularity. So, that means if we try to produce the yarn with 100 number of fibers, so we cannot get less than this irregularity. So, it will be more than this irregularity. So, that will define the index of irregularity, that is performance. So, this is the irregularity. Suppose we are getting a cotton yarn with a counts in such a way that number of fibers in the yarn cross section is 100. So, we will not definitely get the value of say 10.6, we will get the value. So, V actual CV actual will be more than 10.6. So, 10.6 it may be say 10.7 or maybe 11, maybe 12. So, then how to control, how to judge this performance? To judge this performance, we have one parameter which is known as index of irregularity. So, what is that? So, VR is the calculated limit irregularity and V is the actual irregularity of the product. For sliver, suppose we can calculate the limit irregularity by knowing the number of fibers in the cross section, and actual irregularity we can calculate. Then the index of irregularity will be V by VR, the ratio is that. So, I is the index of irregularity which is more than equal to 1. When if it is 1, that means the machine is running perfectly, ideal running, but in actual practice it is more than 1. So, higher the I value, poor will be the performance of the machine. So, that is the condition. So, we have say two machine we can compare, the producing the same product, same from the same fiber, same sliver it is producing, and two draw frame we can compare, or even two ring frame we can compare. So, the machine with higher I value, index of irregularity, that means its performance is less, lower inferior performance, it is poorly performing. Hence, a value unity, that means 1 for the ratio correspond to the limit irregularity best possible yarn produced. So, when the yarn is a best possible yarn or best possible sliver, so in that case you will get the value 1, and higher value of I, more irregular yarn and performance of the spinning machine is low, poor performance. Now, let us try to see one calculation. A 20 kilotex draw frame sliver with CV percent of 1.2 it produced from 5 decitex of polyester fiber. So, index of irregularity of draw frame, what will be the index of irregularity? Now, let us see. So, what index of irregularity we know, and it is from the polyester. So, polyester fiber, for man made fiber we know the relationship is 100 by under root n. So, only thing we have to calculate the, so this is limit, sorry, CV limit. So, VR, this is VR. So, VR we can calculate. So, 20 kilotex, so that means 20,000 tex, okay, and 5 decitex is there of polyester. So, number of fibers in the cross section we will calculate, and from there VR we will calculate, and once the VR is calculated, V is given. So, I will be V by VR. So, that way we will calculate. Okay. Let us see the calculation. So, actual CV is 1.2, sliver linear density is 20 kilotex, 20,000 tex, and fiber linear density is 5 decitex, that means 0.5 tex. The number of fibers in the cross section will be 20,000 divided by 0.5, it will be 40,000. So, number of fibers in the cross section we can calculate, it is a 40,000 fibers are there, and the limit CB of the drop frame sliver will be 100 by n, that is 40,000, it is 0.5. So, index of irregularity of the drop frame we can calculate as 2.5, 1.2 divided by 0.5, 2.4. Now, we can compare with another machine. So, in that case we the performance can be compared. So, this is the limit index of irregularity 2.4. Now, let us see another numerical example. So, here if we see now 20 kilotex is produced from in place of 0.5 it is 0.4, 20 kilotex is produced from 0.4 decitex, and which is producing a CV of say 1.15, 1.15 or 1.1, 1.1. So, what will be the index of irregularity? So, another drop frame which is producing 20 kilotex sliver from 1.1 and producing the sliver of 1.1% CV, and from there can we tell that the drop frame 2, this is drop frame 2 is producing better, it is performing better way, because that it is producing, because of the fact it is producing the drop sliver of lower uniformity, lower actually CV percent. Before coming into conclusion, we must see that the fibers used here is 0.4 decitex, okay, 0.4 decitex. So, in that case we must go do the calculation. So, for drop frame 2, this is for drop frame 1, drop frame 2, number of fibers in the cross section will be 20,000 by 0.4. So, it will be 50,000, 50,000 fibers are there, okay, and here it will be 100 by 50,000, 100 by 50,000 will be 0.44, this is 0. It will be 0.44, and number of fibers will be, what is the number of fibers? 50,000. So, the index of irregularity will be number of this is the CV limit is 0.44 and number of fibers. So, it will be 1.1 divided by 0.44. So, it will become 2.5. So, 2.5 is that. So, that means earlier it was 2.4 which was producing 1.2 CV percent, but here although it is producing 1.2 CV percent, although it is produced, this drop frame 2 is producing 1.1 CV percent, still we cannot tell the its performance is good, because here we are using a finer fiber which is 0.4 decitex and its index of irregularity is 2.5. In earlier case it was 2.4. So, the fact is that the drop frame 2 is actually performing in poor way, poor performance is there. So, draw frame 1 is performing better way. So, that we can compare the performance between two machine running, because the CV% is not the ultimate indication of the performance. It is, although it is a quality wise it is good, the ultimate requirement is good, but machine performance wise we have to calculate the index of irregularity. Now, the addition and reduction of irregularity. So, in any drafting system, any machine we produce, like in carding, in draw frames, ring frame, speed frame, wherever we stretch, we draft, it adds to the irregularity. Every stage the irregularity is added, but in draw frame the beauty is that in draw frame is the only process where we can reduce the irregularity because of the doubling. The same thing happens in the rotor spinning also, so where the back doubling takes place. So, we can actually do correction at the draw frame stage. In the formula given in the limit irregularity, the square of the coefficient of variation is used. Basically, in addition is where we do the basically addition is done based on the, not based on the coefficient of variation we cannot add, but we can add the variance. So, variance can be added, standard deviation square can be added, but also we can add the relative variance. Okay. Relative variance is the that we can add and which is CV% square is called relative variance. Okay. And in term we will use this term only variance. Okay. Relative variance often we use as variance, although variance is the standard deviation square. By using the square of the coefficient of variation, it become possible to add or subtract the irregularity, okay, produced at various stage of yarn production and yarn preparation and spinning, in draw frame, in ring, in speed frame, that we can do. Suppose CV% of sliver is V1 and it is fed to the draw frame which adds irregularity V2 during this process. So, V1 is there and during the process it is adding V2. So, V1 is the input sliver and CV added. So, V output is the output of this machine. So, V is the coefficient variation of the processed sliver. V is, so V is the output. So, in that case what will be the relationship? So, V square V1 square plus V2 square. So, basically it is added in terms of their square. Square of the coefficients. So, V square will be V1 square plus V2 square. And we can reduce it by doubling. So, in draw frame suppose n number of slivers are doubled with a CV of V input. Okay. So, now V CV of sorry. So, in the draw frame we are feeding say n number of slivers, 1, 2, so n number of slivers we are feeding, and CV of individual fiber is V. So, the total CV V input sliver input material of n slivers, it will be actually reduced to V by under root n. That means, the CV percent of input slivers will be reduced. One of the objectives of doubling is to reduce the irregularity. So, we reduce the irregularity because of the fact that the system is that in probabilitically the thick place will be actually superimposed with the thin place. So, that is why it gets the evening out effect. So, if n strands of material each having the same coefficient of variation are doubled, then the coefficient of variation of the combined strand will be CV double strand will be CV of individual strand by under root n, that has already been mentioned here. Now, here you can see the in the draw frame, this is the input sliver and added irregularity V A, and this is V output. Similarly, in draw frame machine we have number of slivers we have number of slivers added. So, V y such n number of slivers, and then it is going to the machine and output slivers. Now, we will let us try to understand with one example. Let us try to understand with an example here. The mass CV of card sliver is 4% and number of doubling at draw frame is 8. So, 1, 2, 3, 4, 5, 6, 7, 8, 8 slivers are doubled. These are 8 slivers are going, and then this is the ruler setting in the draw frame, rulers are there. Now, these 8 slivers are mixed together. So, what happened, each card sliver is 4%. So, 8 slivers are there, that means 4 divided by under root 8 is the CV of input material V I, okay, input material. So, that we can calculate here, and CV is added 3% in the draw frame. So, 3% is added, and also another 3% is added at the roving stage. So, we would like to calculate the CV percent of the roving. So, 8 card slivers with CV percent of each sliver is 4% and doubled. So, 4 by under root 8 will be 1.414, and when CV percent is added, so that is it is doubled. So, CV out, so output material of the draw frame will be CV percent of input in draw frame, which is 1.414, and CV added, which is 3%. So, 1.414 square plus 3 square will be 3.13166, that is the draw frame sliver, and over this over and above there will be 3% added. So, again 3% added. So, what we get? We get the CV out product of the roving is a CV input of the roving, which is 3.13166 3.3166 plus Cb added, which is 4%. So, 3.3166 square plus 3 square, which is under root 20, 4.47% is the Cv percent of the roving. Okay. Now, the variability can be classified into broadly into two parts. One is the periodic variation. So, all traces of irregularity do not show the random distribution. So, variability cannot or it cannot be always random. Sometime the variability is also in a periodic fashion. This is mainly due to the faulty roller or faulty gear, any fault in the rotational component which generates the periodic variation. So, suppose the traces show definite sequence of thick and thin places in the strand of material. These forms of irregularity is called periodic irregularity. So, they have say definite sequence of thick and thin places in the strand of material. They have sequence, definite sequence. Now, this is the sequence here. That is, it will have thick thin places where M is the mean height of the chart, that means mean yarn cross section or mean mass per unit length. A is the amplitude, that is the maximum variability from the mean line. Okay. This can be, this is A, maximum variability, and B is the wavelength. So, repeat length is the B, and A by M is the percent amplitude. Okay. So, that way we express the periodic variation, and based on the length of the periodicity, it is further divided into three classes. So, using the fiber length as the length unit, the periodic variation is actually classified according to their wavelength. If the periodic variation length is that the wavelength is 1 to 10 times of fiber length, then we will call it as short term irregularity. And if the variability, that wavelength is 10 to 100 times of the fiber length, then it is termed as the medium term variability. And if it is the wavelength is more than 100 times, then it is called long term irregularity. So, short term irregularity is always generated at the end product, like if you want to know the irregularity of the sliver. So, the short term irregularity, if it is there, then we normally try to target the front roller, there may be some front roller problem. Okay. But if it is medium term or long term will be maybe at the back, maybe at the blowroom zone. Similarly, for ring frame, if we talk about the short term irregularity, that may generate it within the ring frame, maybe front roller or middle roller. Okay. But if it is medium term, so the back roller may be there, or maybe roving frame, or a long term maybe roving or maybe draw frame. So, that way, so because it gets stretched, depending on the wavelength, we can divide the periodic fault in short, medium and long term. Used this classification is used when actually this classification is used when causes for actually we are causes of the fault is investigated. So, we want to actually identify the fault. Okay. The amplitude of short term variation are generally greater than the long term variation, because why? Because in the long term variation, so in the long term variation is that happens at the back of the earlier process, and that is why that gets stretched and there is a chance of correction. So, amplitude reduces, but short term variation which happens at the end of the fault at the end machine towards the end. So, that amplitude is high, because short term variation they occur at the last machine and have no chance of being reduced by doubling, but in case of long term we have chance to reduce the variability by doubling. Now, how to measure? So, there are different methods of measurement. Okay. Earlier that mechanical method or optical method. So, there are methods, but most popular method is that it is a capacitance type method. In the capacitance method, there is a capacitance plate, parallel plate capacitance is there, and here. So, this is the capacitance plate. Parallel plate capacitance, and now the sliver or any material, it is moving through this, uneven material is moving through this. Now, here what happened, in the standard length of capacitance plate is 1 centimeter. 1 centimeter is the standard length, and within this zone the capacitance value is dependent on, it is proportional to the mass of the material present. That capacitance value, we are not calculating the mass, we are calculating the capacitance from this, which is proportional to the mass. So, capacitance is equal to K mass of the material. And what is the material length? Length is 1 centimeter. That means mass per centimeter we are getting here. But we cannot measure K value here. K is unknown, and the value of K depends on many unknown factors like type of fiber or what type and capacitance of fiber, that material, polymer, type of polymer, diameter of fiber or moisture content. So, many other factors are there, but it is proportional to the quantity of material content. Okay. Here we are measuring, so at this stage we are measuring mass. So, capacitance C1, which is equal to K M1, sorry. So, at this stage we are measuring capacitance 1 K M1. Now, next section the material is moving, the sliver or yarn is moving. Next section, and it is moving at a speed of say V delivery speed, that is known delivery speed. Now, at certain time t, this portion will come out here and new portion will enter here, and that the time of movement of 1 centimeter, time of movement of 1 centimeter is dependent on the delivery speed. So, time, what is the after which time, that is time lapse. So, based on that the data acquisition system is set. So, we know the speed of delivery and data will be taken exactly after delta t time, where 1 centimeter is actually moved. This we cannot repeat the section. So, next section has come here and new section will be, now let us see, 1 centimeter is there. Now, this is another material 1 centimeter, 1 centimeter. So, this material is there, these are the same material, these are the segment, different segments. So, green segment has completed, then just cut कर इसका, क्या हुआ? Okay. The green section has completed. Now, the next section will be blue section. This is the blue section is coming. Again 1 centimeter is entering here after time delta t. So, in this way we will get the capacitance 2 by k m2. Similarly, we will get k m n. So, in this way we will get large number of capacitance value. Now, here can we calculate the mean mass per length, mass per centimeter? Answer is no. We cannot calculate the, we cannot measure the mass per unit length. The what we can measure, even we cannot measure the standard deviation. The standard deviation, in that if we try to measure the standard deviation, if we know the, if we come back to that formula, standard deviation formula, the unknown factor k will remain both for mass per unit length and standard deviation. But if we try to measure the Cb percent or u percent, this k will be present both in numerator and denominator. So, k value will get cancelled out. So, that is why in electronic type tester we cannot measure the mass per unit length or standard deviation, that is we express the variability in terms of C percent or U percent. So, we are not measuring the mass per unit length, but we are measuring the capacitance, we are measuring the capacitance, and which indirectly shows the mass per unit length, and with the unknown constant. So, unknown constant has to be eliminated. So, a chance of in the mass of dielectric non-conductive material. So, this is a change, that if there is a change in the dielectric constant, so the capacitance will change. Capacitance is proportional to the mass of the material present, as I have mentioned. If the material is drawn at a constant speed through the condenser continuously, the change in capacitance will follow the mass variation. Here the unit length is 1 centimeter, that is the length of the capacitor, and here from there you can see that we are getting the U%. We get for a yarn or sliver, suppose we get U% of say 10%, and the machine is running at speed of say 400 meter per minute, and we are running it for 1 minute. 1 minute it is running, and what does it mean physically? 10% U%. The physically, if we try to understand, we can say, suppose we have the sliver or yarn of say 400 meter, same 400 meter is given to me. After testing, the machine is showing 10%. So, 400 meter is given. So, what we are doing, we will be actually cutting the physically, if we try to measure, if we try to reach to 10%, what we will be doing? We will be cutting this yarn into small pieces, each of 1 centimeter length, and theoretically we can measure the mass using microbalance. So, this will be M1, M2, M3, and 400 meter and 1 centimeter length, that means multiplied by 100, there will be 40,000 pieces, okay, and last one will be M 40,000. 40,000 pieces will be there. So, M1, M2, M3. Now, this 40,000 pieces, what we are doing? We are using the microbalance and taking the mass of each and every pieces, and this every pieces we are taking mass, and then we are calculating the standard deviation of the mass per, and if we calculate the percentage mean not standard deviation, it is percentage mean deviation we have to calculate. So, mean deviation we calculate, then mean we calculate, and we can calculate percent mean deviation of all this 40,000. Then we must get 10%. 10% we should get if we count, if we measure correctly. So, this is the theoretical concept of U% or CV% if you want, we can get use the standard deviation, but practically this is not possible. Practically it is not possible. We use indirect method of electronic capacitance type test method. Now, you can see if the material is drawn at constant speed through the capacitance continuously, the changes of capacitance will actually follow this type of curve, okay? Mass per unit length variation that will follow, and U% and CV% can be calculated. So, this is the total summation here. So, using this formula we can get the U% and CV%, that is effectively it is a percent mean deviation and the standard deviation we can calculate from each and every point, and CV% is, if it is normal distribution, then CV% will be equal to 1.2 multiplied by U%. That means, CV% value we get always higher than U% value. So, in this electronic capacitance type method of measurement, we get both CV% and U%, and CV% value is higher than U%, it is approximately 1.25 value, but it is not always in actual case it may not be 1.25 always. Okay. The next one is the diagram. What is diagram? Diagram is not literally meaning is any picture. It is not that. Here in electronic type capacitance tester, we use the term diagram to express the curve which follows the mass variation. Okay. So, the graphical representation of mass per unit length variation along the length of sliver, roving or yarn refers to as a diagram. So, this is the length, and here the mass per unit length variation is there. Now, when the machine the system starts, the capacitance type method it starts. So, the system records the variation. So, here we will see that it is variation. Here at 0 point it is a mean value, and with the reference it is going with the time, okay, with the length is there. X axis is length, y axis is the mass variation. So, it indicates the nature of variability present in the material. So, how the material is actually varying the its mass per unit length. So, if we see these two curve, here the mass per unit length variation is less, okay, with, and here it is wide variation. So, from this we can have actually overall idea of mass per unit length, we can get some idea. Now, here the main point is that how do we get the mean value? Here mean value we have got, and along the mean value we are getting this, we are plotting here. Now, when the sensor starts, this is the capacitance type sensor, and when it is the material is flowing. So, the material is moving through this, the yarn, sliver or roving. The capacitance type sensor does not have value, reference value, which is the mean value. So, that what it does, initially for some time, typically around 10 second, the total screen, a computer screen becomes blank, no data you will get. So, after 10 second we will have sufficient data is accumulated, and immediately it calculates the mean. So, mean is placed at 0 point, and then it starts plotting. So, it goes in this fashion, and from there we can get overall picture of the variability. The normal diagram is that the normal diagram represents the graphical plot of the basic mass per unit length variation of strand of fibers over length. This is the normal diagram. The reference length for the mass value is 1 centimeter, and cut length diagram is that. So, what is that? We can use the cut length diagram like 1 centimeter, 3 centimeter, 10 centimeter, 100 meter, these are the called cut length diagram. Now, how do we get cut length diagram? Now, again, as I have already mentioned, this is the parallel plate, and here the length is 1 centimeter, and as the material moves through this, depending on the speed and data acquisition rate, we get the value. So, typically initially we measure the mass at each and every centimeter, but if we say slow down, so after 100 such data, if we take the mean, so if you slow down the rate of acquisition by 100 times, that means after 1 meter it will actually add 1 meter to 100 data. So, then we get per meter, okay, variability. So, it will take the data, it will add to all this. So, you will get that value. So, it is called cut length diagram. This is the cut length diagram for 1 meter. This is the cut length, where you will see the variability is averaged out. So, variability is averaged out. If we take it for 3 meters, this is for 1 meter. If we take it for 3 meter, this will be further smoothening, it will be further smooth. Okay. So, auto leveler, we can actually check the functioning of auto leveler. Now, let us do one example. So, draw a typical diagram of 40 any cotton yarn produced with front roller eccentric front roller drop at the drop frame. Assume all the relevant data. So, that we have to draw a typical diagram. Assume the front roller diameter of drop frame is 2.54 centimeter and draft at roving frame and ring frame are 10 and 40. Okay. 10 and 40, these are our assumptions, we can assume anything. The wavelength of periodic fault generated at the drop frame sliver, because it is a front roller is eccentric. So, the wavelength generated at drop frame will be the circumference of the front roller, which is pi 2.5, that is a diameter, that much centimeter, and then it will be stretched by 10 times at roving frame and 40 times at ring frame. So, this multiplied by 10 multiplied by 40, that will be the, this will be the wavelength of yarn. So, this is at roving and it is at yarn. So, if we see this much centimeter, so it will be 32 meter. So, 32 meter is the wavelength of periodic fault of yarn. So, we can draw the typical diagram. So, this is the typical diagram of yarn, where the variability in the diagram is there, mass variability in this fashion it will be. So, here you will see the mass this is the short term variability due to the fibers movement and all this, but due to the roller eccentricity this type of periodic varicity will be there. From there also, from the diagram also, we can identify whether the fault is periodic or not. Okay. And we can get histogram here, which is actually a frequency distribution of diagram, okay, of mass per unit length variation in sliver, from which one can identify whether the overall thick and thin places are evenly distributed or not. So, here we can see the overall thick thin places, whether it is evenly distributed or none, that we can get here. Now, from diagram what do we get? So, we get different information which we may not get from other instrument, other type of expression. One is that long term wavelength variation, even a periodic variation which spectrogram cannot confirm. Like in spectrogram, we get the, in a spectrum we will discuss, we get the periodic variation, but if it is very long term variation, then the spectrogram may not be able to confirm, because the number of times it repeats will be small. Like suppose we are testing in the spectrogram, in the electronic tester like Worcester tester, we test Evenness tester, say 400 meter. If the wavelength is say 200, then number of repeat will be 2, which spectrogram will not be able to identify. But in case of diagram, diagram will show a clear picture of variability like this. This will be the diagram. So, this is one repeat, so 200 meter, and then it will go like this. So, we can make out the whether there is any periodic variation or is there or not, a very long term variation, that the spectrogram will not be able to identify. The spectrogram part we will discuss subsequently. Extreme thick and thin places. Extreme thick and thin places spectrogram will definitely not be able to identify, because there is it is not the periodic fault, and also it will not be able to identify anywhere. So, how suppose one in the draw frame or in any other, in the roving frame, what happened, there is a split, sliver split, or in the draw frame the double sliver has come. So, from there what we can do, in the diagram we can get this is the normal diagram, suddenly it is increased and we are suddenly we get this thing, and then normal diagram. Here at this point, if there is a sudden increase in the mass per unit length and it goes for some time, that means there is a problem at the processing stage, where the slivers have been doubled, or it may come in this fashion at the lower side if there is a sliver split. So, from there we can identify the processing performance of any this is not due to the machine fault, but due to the environmental fault or due to the running workers fault may be there. So, changes and the step change, slow change and step change can be actually from the mean value we can get from the diagram. In many cases it confirms the numerical value of the instrument also. So, in a step change we can see, suppose there is a step change is there. So, this will show the running performance, because there is a split due to the this doubling, okay, and slow change will be there. this type of change is also possible. So, where we can identify the long term variability. Okay. So, we will stop here, and next session we will start another important aspect, which is spectrogram. Till then, thank you.